So this is obvious manipulations. This is joint with Pete over there. And as you probably guessed from the title, this is work that's motivated by Sheng Wu's paper. So this really influential paper. It's been mentioned a bunch of times at this conference. But Sheng Wu's looking at obviously strategy-proof mechanisms. So you're considering a number of different strategy-proof mechanisms. Which one is clear that is strategy-proof? We're actually interested in the opposite direction. So there's a lot of situations, where there may not exist a strategy-proof mechanism. So, for example, in two-side matching problems, there doesn't exist any stable and strategy-proof mechanism. And then there's a lot of other situations where strategy-proofness imposes a constraint on what we can accomplish. So this is something like school assignment, where by limiting ourselves to a strategy-proof or stable mechanism, we're losing out on efficiency. So we want to take this in the opposite direction, that when we're considering mechanism, we want to expand it and consider mechanisms that are manipulable, but maybe mechanisms where it's not so obvious how to manipulate them. And that way, maybe we're not worried so much about implementation issues. Okay. So this is a quote. This is from Eric Budish and Kessler. And I just love this quote because to me, it captures exactly what we're going for in this context. He's talking about the competitive equilibrium from equal incomes in the course assignment situation. And what they say is the kinds of profitable manipulations that were found in extensive computational exploration are non-intuitive. Since there's a risk to misreporting, one is no longer guaranteed one's most preferred affordable schedule at the realized prices, and the benefits of misreporting are difficult, if not impossible, to realize. Then they go on to say, if either of the authors of this paper were participating, we would report truthfully. Okay? So to me, at least at an intuitive level, this is what it's getting at. There's some types of mechanisms where a manipulation both requires a lot of understanding of the process, a lot of information about the other preferences and the outcome, and not only that, exposes you to potentially very harmful outcomes. Others mechanisms where none of this is true. And this is sort of as a motivating notion of what we're trying to use to distinguish between what we're going to call obvious manipulations and non-obvious manipulations. Okay? So in the context that we'll return to later, sort of the most salient to us is a school assignment. And here there's sort of two very clear manipulable mechanisms, the Boston mechanisms and the school proposing deferred acceptance. And at least for us intuitively, the Boston is really easy to manipulate and the school proposing deferred acceptance is not. And so we're going to use this as kind of a guideline in our taxonomy between the two. Right? So the Boston mechanism, sometimes called the immediate acceptance algorithm, is basically we're trying to assign as many students as possible to their top school. And so effectively, all that matters is what school you rank first. So in particular, you can have a neighborhood school, you have highest priority, but if you don't rank that school first, and a lot of people rank it first, you're going to lose out on that school. Okay? And so there's a very clear manipulation you have to take. Basically, the idea is that you want to rank the best school you can get into first. And this is very salient to parents. So there was one Boston group that was so organized they took minutes. And so this is a quote from the minutes. One school choice strategy is to find a school you like that is underscribed and put as a top choice, or to find a school that you like that is popular and put as a first choice, and find a school that's less popular for a safe second choice. Okay? So this is sort of a manipulation that a parent group, presumably no experts, can see. It's very clear. And you can look empirically, people do behave exactly in this way. Okay? So compare this instead to the school proposing deferred acceptance algorithm. So this is where we have the schools proposing to the students. And so as we know, this is manipulatable from the perspective of the students. And so we can see this in a very trivial example. This is the most trivial example you'll see all weekend. We just have two students, I and J, two schools, A and B. And so if we do the school proposing, school A proposes to J, school B proposes to I, and that's it. It stops. So that's our school's proposing assignment. Now, this can be manipulated by either student, but roughly speaking, for any of these, the way you manipulate the other side of the deferred acceptance algorithm is you identify the set of stable assignments, and then you truncate your preferences by only ranking your most preferred stable assignment first. So here, there's two stable assignments for I. He can either get A or B, and so if we do the school proposing, he's going to get B, and so his manipulation is to declare that B is unacceptable. So if he does this, now, when school B applies to I rejects him, and so B goes on to apply to J, who rejects A, who then goes on to apply to I, and so I gets his favorite school. Okay? So school proposing is definitely manipulable by the students, right? But it's somehow different from the Boston mechanism in at least two different dimensions. This person, he's got to be able to calculate the set of stable assignments, but not just that, he's exposing himself to risk. So what if he's wrong about student J? So here we have student J prefers B to A, but what if he's wrong? If J instead ranks A first and B second, then now I is going to be unassigned. Right? They're somehow different, so it's not just that it requires more knowledge, it's now exposing himself to worst possible outcomes. Right? So this is what we kind of think of as our guideline. So our goal here is to formalize what we mean by an obvious manipulation and to create a taxonomy of different mechanisms. Okay? So these are sort of our only definitions. We've got just a normal definition of strategy proofness. Strategy proofness just says that revealing your type is a weakly dominant strategy. And we call an alternative report, theta prime, a manipulation if there exists some profile where you get strictly higher payoff by reporting theta prime to theta. Okay? Just somewhere, anywhere. Okay? And so this is going to be our definition of an obvious manipulation. Okay? So we're going to say that theta prime is an obvious manipulation if either the worst case under theta prime is better than the worst case under theta, or else if the best case under theta prime is strictly better than the best case under theta. Okay? So hopefully it's obvious that a manipulation is a manipulation. Okay? If there's some outcome with the range is strictly better, there has to be a profile where you do strictly better misreporting your preferences. Okay? So kind of what led us to this, what we like about this, I'll come to a formal characterization of this, motivation of this later on, but what we liked about this is that, first of all, it doesn't require any information about distributions. You don't have to have anything about beliefs or priors or common priors or anything like this. This is just figuring out what are the range of possible outcomes. Okay? And so we think of this as being consistent with the Wilson doctrine. Second is we want something that is sort of tractable and easy to calculate and salient. And so here it's typically much easier to figure out the min and the max of a range than it is to figure out for every possible preference profile is there a profitable deviation. And the last one we're not going to formalize, but we think of in some sense as capturing downside risk. If the worst case outcome is better, we think in some ways that we've sort of eliminated downside risk. And we deliberately don't want to model preferences over uncertainty, but that's at least what we're kind of thinking about. Okay. So this might look to you like max-min preferences. This is not max-min preferences. So there's a min and max here, but we're not making any assumption on the student preferences. Okay? So this is not somebody who's trying to maximize their worst case scenario. This isn't even getting at to what should the person do. We're thinking before we ask what should the person do, should the person manipulate it, we're first asking, is it clear to the person that this mechanism can be manipulated? So even in the Boston mechanism, it's not the case that you always want to rank your neighborhood school first. If the schools ahead of it are undersubscribed, then you don't want to change that. And so we're thinking before you think about do I manipulate it, you're first asking, can I manipulate it? So for us, this is not about changing the preference. This is instead something about salience. Right? All right, so I knew I was going to be around computer science people, so this is my attempt at a fancy graphic on this. I'm sure I'm going to be ashamed of the next one. But the way we're going to characterize this is actually think about this as the mechanism from the perspective of the agent is just a black box. I literally don't tell the agent what the mechanism is. Okay? Instead, what I'm going to tell them is I'm going to tell them the range of possible outcomes for any report you might make. Okay? So if you know Xingu's paper, this is exactly the same as a cognitively limited agent. It's just he's considering a more complicated, extensive form mechanisms, whereas in direct mechanisms, you can view this. You could call this, he cannot engage in contingent reasoning, but for us, we're just going to say he doesn't even know what the mechanism is. Okay, but he knows the range of outcomes. And we think this captures the school assignment really well because this is a parent group that has collected the data. They know what the other people in their neighborhood have reported and they know their outcomes, but they don't actually fully understand the mechanism. Right? And so we're going to say if an agent can figure out that they can manipulate the mechanism without even knowing what the mechanism is, then that's an obvious manipulation. Okay, that's what we're going for. Okay? So this is characterization, so it's not going to be surprising what the result is. An agent can only detect if he can manipulate the mechanism if the best case is better or the worst case is better. Those are the only two situations. And sort of once you get the setup, this is a proof by picture. If I give you the ranges here, so this is under the true report, I've got the red line under the alternate blue. Theta prime could be a manipulation, it could not be a manipulation. I don't know, I don't have enough information. Okay? Also, if I give you a whole, well, it could have been replaced by something better or something worse. That could be a manipulation, maybe it's not. But if I give you a situation like this, so here's a range. I haven't told you what this mechanism is, but you know you can manipulate this mechanism. Whatever profile generated that dot has to be better under the alternative report than under your true preferences. So without even knowing what the mechanism is, you know you can manipulate it, and so we're going to call that an obvious manipulation. Okay? Same way here. From this range of outcomes, you know that you can manipulate this without even knowing what the mechanism is. Right? Okay, so this is no surprise. The Boston mechanism is obviously manipulable, and so this is an easy proof by example. And so here's a real simple situation where I's neighborhood school is B, meaning I has the highest priority at B, but he doesn't want B, he wants A instead. And the problem for him is that A might be a highly demanded school. So if he does his true preferences here, he gets rejected by A, but then J steals his spot at B and he ends up with C. Whereas if he were to rank B first, he's going to be guaranteed to get B. And so there's an instance that we know the worst possible outcome from your true preferences is worse than if you misreport and rank B first. So ranking B first is an obvious manipulation. Okay? So what we're really interested in is, or at least what I'm interested in, is the school assignment. We have this tension of there's no strategy proof mechanism that's fair and Pareto efficient. And so the natural thing to do is sort of start with a fair assignment and then Pareto improve it to reach the frontier. And so what we'll be able to show is we'll call this a stable dominating mechanism, anything that Pareto improves any stable assignment. And so there's actually, so this also includes all the stable mechanisms you can think of. So this is the student proposing deferred acceptance, school proposing deferred acceptance, Keston's efficiency adjusted deferred acceptance mechanism with the deferred acceptance with compensation changes, all these. And so all the different ways that you can also Pareto improve it. And so one of our main theorems is that no stable dominating mechanism is going to be obviously manipulatable, right? And so what we think of is that exactly what we want, which is to take an inefficient assignment and Pareto improve it. If we restrict ourselves to strategy-proof mechanisms, we can't achieve this. But if we allow ourselves sort of mechanisms that are manipulatable, but maybe not obviously so, we can achieve better outcomes. Right? And so this is sort of, again, is sort of not a hard proof, but we just have to figure out what's the worst possible outcome under the deferred acceptance algorithm. And so all that matters here, so you don't really need to pay attention to the notation, but we're going to, we can think about if your first assignment is your first assignment the worst possible outcome, well, it depends on whether you have one of the highest Q priorities. So if we're going to call U of A the set of students that are ranked higher than you at school A, and if U of A is less than the cardinality of that set is less than the capacity, then obviously you can't end up with the worst, anything worse than A. Okay? So with two schools, it's slightly more complicated. So here's a guy where there's more people ranked ahead of him at A, and there's more people ranked ahead of him at B, and A is his favorite school and B is his second. So could he end up worse than B? Well, not necessarily. What matters is the intersection of those two sets. Somebody can only get one assignment, so as long as there's enough overlap between these two sets, you can't end up worse than school B. And this suggests exactly what's going to matter here is a Hall's condition on the marriage theorem. We're just going to consider the set of students that are ranked ahead of you, and if we can match those to the schools you want, then you're going to end up with potentially a worse school than that. But if there's no way of matching students ahead of you, then you can't end up with a school that's worse than that. Right? So Halls we've probably seen at some point, but there's this sort of obvious necessary condition that the neighborhood for every set has to be at least as many people as in the neighborhood. And what's cool about the theorem is that that's also a sufficient condition. And so here, what we're going to do is we're just going to construct a graph where we have an edge between every school and every student that's ranked higher than you at that school. And we go down your list, and the first place where Hall's condition is violated is going to be your worst possible school. Right? So here, A is this guy's favorite school. Hall's condition is satisfied because J is ranked higher than him. And so if J ranks A first, then I is not going to get A. So his worst possible assignment is worse than A. Now we consider A and B. B is his second favorite school. We look at all the students that are ranked higher than him that creates some sort of graph. Here again, Hall's condition is satisfied, so it's easy to construct a perfect matching. And so now we know that if J ranks A first, K ranks B first, then I is going to get a school worse than B. We add C, we get a more complicated graph, but now we have a violation of Hall's condition, which is to say J is the only student ranked higher than him at A or C. J can only go to one of those, so now we know that the worst possible school under the deferred acceptance is C. It's the first place where the Hall's condition is violated, right? And so that's the basic result. The reason why this completes the proof is that everything we've said about this in the construction of the worst possible case is Pareto efficient. So for any Pareto stable dominating mechanism, the exact same thing applies. Okay? So the worst possible place is exactly the same under deferred acceptance or exactly the same under any stable dominating mechanism. Best possible case, obviously, you get into your favorite school. And so the range is exactly the same as to these things. And so any manipulation is not going to be an obvious one. Right? That's the basic idea. Okay, so this allows us to sort of very quickly, we can change some classic results. So one of the classic results from Roth is that there exists no mechanisms of both stable and strategy proof. There's the sum as econometrica, which says that the core is essentially single valued. And so none of these apply as long as we relax strategy proofness and consider instead not obviously manipulable mechanisms. So now we know that any stable mechanism is going to be both individually rational, Pareto efficient, and not obviously manipulable. Okay? So similarly, so we can apply this to auctions as well. It doesn't have to be restricted to non-transferable utility, but the pay-as-you-bid auction is going to be obviously manipulable. Any strategy you can think of, there's some situation where you would have been better off having a lower bid. Hopefully it's kind of clear. But what's a little bit more interesting, and this is, again, it's just sort of this, neither of these results are hard, it's just hopefully matches our intuition. A uniform price auction is not going to be obviously manipulable. Your best and worst case scenario are going to be the same from any misreport or any under the truth. Right? So we can strengthen, or I guess not really strengthen, but sort of a different interpretation of something like the Myerson-Satterthwaite result. So here we know that there doesn't exist any efficient, individually rational, and weakly budget balanced mechanism. And so now we can strengthen that. Not only is the mechanism not going to be strategy proof, but it's going to be obvious to manipulate. And here again, the idea is, what if the buyer has value 1, seller has value 0? There has to be some price in between. And one of them has an alternative that gives them a strictly higher potential profit, whichever one. Okay? So these results, once the notion is very tractable, and so all these theorems are actually very easy, and we actually think of this as a good part about the paper, because what we're looking for is a nice tractable way of divvying up these different things. Right? Okay, so that's the basic idea. So we're trying to formalize what we mean by obvious. We want to consider, instead of strategy proofness, we want to take manipulations, and comes up with a way of classifying a mechanism as a non-strategy proof mechanism as either obvious to manipulate or not. Okay, and so you can apply this basically to as many different situations as you want. But we think perhaps most interesting is school assignment, where there's a real tension between fairness and efficiency and strategy proofness, some very strong impossibility results. Okay. Thank you very much.
We have time for a few questions.
Okay.
I have one.
Okay, sure.
So do you know the ratio between this not easily manipulable mechanisms versus most strategies mechanisms, performance further, whatever object?
You mean like how much improvement? Yeah, so it's obviously situation dependent. But so, for example, in New York City, there's a 7% efficiency loss. So we can Pareto improve 7% of all the student assignments with a mechanism that is efficient. Pareto dominates the fair assignment, not strategy proof, but it's not obvious how to manipulate. And this, sort of more egocentric, so this is like the Keston's efficiency adjusted deferred acceptance. And it kind of hopefully matches. It's a very complicated algorithm. It's hard to figure out. And it's kind of, to me, it's not very, I'm not convinced that parents can figure out how to game it. Okay.
Other questions? Okay, let's thank